which typically are considered in negative way, like fault, imperfections, shortcoming, scratch, error, mistake, so it's like something bad. But we will see how we can manage these defects to do nanotechnologies. So use complex of defects and manage these defects, making them bigger or smaller to do nanotechnologies in dielectric media. And we will use lasers for that. And so this is outline of my lecture. So we'll follow these steps. First, we consider what kind of defects are present in solids, how they can be managed by pressure P and temperature T. Then we will consider a simple case, quite simple case of laser hyperblocking of silicon and how the impurities, defects like impurities, can be managed by temperature inside silicon. Then we'll proceed to photogeneration of defects using lasers and consider how lasers are ultrashort-pulse lasers, which we use in our studies, how they can be delivered to some point inside the electric medium, how they produce plasma. Plasma evolves later, and finally this results in atomistic transformations. We will consider case of diamond, and finally we'll go to a new mechanism of ultrashort-pulse laser nanopatterning. So how we can produce nanostructures in transparent media using ultrashort lasers. Okay. Slightly a little bit disturbed, but I came from Moscow, which is somewhat to the north, and through Dubai to this auditorium. So quite a long way to go. Maybe some of you later will come for training to our institute to do laser research, maybe PhD research or something like that. Yeah, welcome. So I'm from Leibniz Physical Institute, which is the oldest physical institute in Russia, which associated with the name of Peter Lebedev, who was the inventor of light pressure in 19th century. Since that time, this is the old building constructed maybe in the middle of 20th century. Now there are other buildings quite contemporary like this one, but this is old one. And this is academician Basov. I will talk a little bit because he was inventor of laser and we some kind of continued his traditions. Actually, in 20th century, there were a number of Nobel Prize winners from our institute. Three of these persons, Cherenkov, Frank, and Tam, they got Nobel Prize for Cherenkov effect, for effect of emission of light when some charged particle, a relativistic charged particle, enters another medium, just crosses the boundary between two media. Okay, Basov and Prokhorov, some years later, Basov and Prokhorov have got the Nobel Prize for lasers, along with American scientists, Towns. Later, some years later, Andrei Sakharov has got Nobel Prize for Peace. Surprisingly, he was inventor of igniter to thermonuclear bomb in Russia. So Nobel Prize for Peace looks a little bit strange in this case because thermonuclear bomb and Nobel Prize for Peace is a little bit different things. And finally, Finally, Vitaly Ginzburg has got a Nobel Prize for superconductivity in our century, but quite close to the 20s. A little bit more about academician Basel, because this year we have 100th anniversary since his birth. So he has got, as I talked, he has got Nobel Prize for invention of lasers. He was academician and director of our institute for many years. Now he's passed away for 20 years ago. But since our division in institute is called Basel division. Many years ago, like 70 years ago, Basel and Prokhorov theoretically demonstrated the possibility of stimulated emission in systems like ammonium molecule, and they have predicted that it's possible to produce inversion of populations by microwave pumping in such systems. If this is 3-level system, so spectrum contains 3 levels. This is some kind of young Basov and Prokhorov. So this is some kind of the sketches of this stuff. So the first, this is the doctor degree of academician Basov. It's called molecular oscillator. So the system was quite simple or even primitive in that case. So every Nobel Prize starts from something very simple. And I would encourage you to do our research very intensively, to continue from this stuff to Nobel Prize in the future. Okay, so this is the procedure when these guys, Basov, Prokhorov, Towns, Basov and Prokhorov got Nobel Prize for fundamental work in the field of quantum electronics. And actually lasers, light amplified emission, stimulated emission of radiation. This is abbreviation. And finally, these kind of systems were proposed in that years. So these are first laser systems, very primitive ones. These kind of systems, and these are now big laser systems producing kilojoules or even megajoules of energy in each pulse for thermonuclear synthesis and stuff like that. Okay, and in our laboratory we will work with nanotechnologies. So we are using lasers for nanophysics and biomedicine. So this is equipment we use in our labs. Different types of lasers producing femtosecond and picosecond laser pulses. Femtosecond means this is 1 billionth part of 1 millionth part of second. 10 to the minus 15th part of second. We use different characterization systems, electron microscopy, different kinds of spectroscopy and microspectroscopy, just optical microspectrometers, confocal Raman microspectrometers, and infrared systems too. So let's start with defects. In solids, there is a lot of different defects which could be related to electronic disorder. So this could be some electronic or other charges trapped in these systems, in semiconductors or oxides. But we will be more interested in intrinsic defects, ionic defects like Frenkel pairs. This is intrinsic defect consisting of vacancy and interstitial. So if we have one atom missing in its right position, its side, it goes in between in some wrong position, and it produces vacancy in its side and interstitial in between. So these kind of defects could be anionic, like in fluorides or fluorides and oxides. And I will show how we're using this in our studies. And this could be cationic friendly pairs, like silver ion or atom in, yes. And another type of point defects is Schottky vacancy defects. So vacancy is just one position, one empty site. So on surface, the empty, quantized empty position could be jumping in the lattice, producing just empty site in the lattice, and it's called just vacancy without interstitial, so without any atom or ion in wrong position. So these are Schottky vacancy defects, and they're typical for alkali halides, cesium halides, and there are other defects, point defects, because there are also two-dimensional defects like dislocations and even three-dimensional defects. But in this lecture, I will talk only about point defects. So defects related to one missing side in the lattice or their small complexes. So if we talk now about impurity point defects, so some foreign or other atom which is not typical for this lattice entering the lattice, these impurity point defects could be substitutional or embedded. Substitutional means they occupy a position of intrinsic atoms, and embedded they're just coming into nanopores in the lattice. The impurity defects could be donor if we have the impurity atom have extra electrons comparing to lattice atoms. For example, in silicon, in silicon we have 4 electrons, 4 valence electrons for each silicon atom, and nitrogen atom with 5 electrons in occupying substitutional position have 1 extra electron, and this electron can travel in the lattice producing electrical conductivity. So nitrogen atoms come as donor defect, donor giving one electron. For example, boron, which has 3 electrons, on opposite it takes 1 electron from silicon and producing hole. So the just absent electron in the lattice. Okay, so the nitrogen appears as a donor, and boron appears as an acceptor. But there are also isoelectronic effects. For example, carbon or in silicon lattice, carbon could be isoelectronic defect, which should be isoelectronic impurity, because carbon and silicon, they have the same number of valent electrons. The point defects could be neutral or charged, for example, and they could be vacancies or interstitials. And donor defects, they occupy in band structure, they occupy position close to the conduction band, so they can give electrons to conduction band through heating or light illumination. And acceptor states, they are occupying positions close to the top of the valence band, and they electron can come in these states from valence band. So in valence band they produce holes, the charge carriers like holes. Point defects, if we talk about intrinsic or even impurity point defects, intrinsic defects, yeah, in this case, like Frankel pairs, vacancy, interstitial, or Schottky defects, they can be reduced through thermal agitation of atom from its right position in the lattice. So through such excitation, it comes to interstitial positions, and atom can travel in the lattice through small activation barrier. And initially, to produce interstitial and vacancy, the barrier should be atom should overcome the large barrier, and this barrier is typically about 1 electron volt. This is simple equations showing how in thermal equilibrium Frankel pairs, vacancy, interstitial, and all Schottky vacancies can be produced as a function of temperature, and about the diffusion and trapping and so on. In our work, we'll go through another vision of point defects and their clusters. So we are talking about defect engineering, so management of defects to make nanotechnologies in dielectrics. For example, in natural diamonds or even synthetic ones, there are big clusters of defects. You can see here, so the carbon atoms of diamond lattice, these are gray circles, and here we have one nitrogen introduced in the lattice, black one, two nitrogen atoms, the double end center, four nitrogen atoms with vacancy in the center, and one nitrogen atoms and vacancy center in NP center, nitrogen vacancy, and so on. So there is a big variety of defects, even in diamond, with each extra rigid lattice. You know, the diamond is probably the hardest material in the world through the other materials. And it has very rigid, strong lattice, and even such lattice, the big variety of complex defects are present. These defects can be visualized for example, in diamonds through their emission. So they occupy positions defect in the band gap between conduction band and valence band, and they can be excited and produce luminescence. And in nitrogen, such luminescence can take the range from UV to near infrared, depending on what kind of defect we have here. And so they can be visualized through luminescence. There is opportunity to manage nitrogen defects in diamond, using high pressures and temperatures, T. If we start just from very simple atomic impurity defects, just one nitrogen atom occupying the position of carbon in the diamond lattice. And if we increase temperature or increase pressure, we will go to condensation, to increase of size of defects. So defects are proceeding through atomic transformation, combining in two atoms, for example, and two atoms joined by vacancy, and three atoms joined by vacancy, four atoms joined by vacancy, and so on and so on. Even in big aggregates and two-dimensional defects, but eventually, and this is thermal oxidation, so increasing temperature helps atoms to move more freely in the lattice and make these reactions. Also, the increasing temperature works as an enthalpy factor. So enthalpy factor means larger aggregates. They are more advantageous energetically because similar atoms are combined together. So the lattice energy becomes reduced, and this is more advantageous. But once we increase temperature more, dissociation of defects of these complexes occurs into simple defects like nitrogen atoms because of increasing entropic factor. Entropic factor means at high temperatures more defects are more advantageous compared to larger defects. So we can see that high pressure increases the concentration of larger defects, and temperature goes in non-monotonic way. Initially increases size of color centers of these defects, and then decreases at higher temperatures. So this is some kind of stationary pressure temperature management of defects, but it's actually not do anything with nanotechnology because we have a big piece of we have diamond, we have stationary bulk heating of this material, so we cannot produce nanostructures inside. We can produce centers, but these centers will be produced everywhere, and we want nanotechnologies. And for that, we should use lasers because lasers can be focused in specific necessary point inside transport material. Let's go to this part. No, we'll talk a little bit. We will see how lasers and stationary heating can be used for nanotechnologies in the case of silicon. Silicon is some kind of material resembling diamond, so the crystalline lattice is very similar, but it's not transparent in visible range, it's transparent in infrared, and now our new experiments are focused on a modification of silicon in its bulk. But here we will talk about thermal activation of sulfur impurities in silicon for infrared absorbance and terahertz detection. Since 70s, 70 years of last century, it was known that sulfur can dope silicon through ion implantation, so we can introduce donor sulfur impurities into silicon. We can produce atomic centers, diatomic centers, and cluster centers like this. And these centers make very important change in silicon properties. Typically, silicon is blind in infrared range. So silicon photodetectors, they operate only in visible range, and infrared range they are blind, they cannot detect anything because of their band gap. But if we introduce these sulfur impurities into its structure, sulfur, as you remember, donor impurities occupy positions close to the conduction band, and small infrared photons can promote electrons from sulfur to conduction band. So there is a photoconductivity response of hyperdoped silicon. And in the 70s it was observed that photoconductivity can be in such materials can occur up to 7 micrometers. So silicon becomes very interesting material because of this technology. It becomes very interesting material for infrared detection of rocket engines, of for night vision, for example, like bioimaging and night vision. So can be used for in military or in technology for different purposes. And this is one material which can cover the range from ultraviolet to deep infrared. So later, after ion implantation, it also modifies just the surface layer, but later another technology was introduced, which is called laser microtexturing and hyperdoping. It was demonstrated by people from Harvard University in the United States. It's exposure of silicon surface by femtosecond lasers produce microstructures, and microstructures are doped with sulfur. They used sulfur gases like sulfur hexafluoride and other gases to the gas molecules, when they're hitting the hot silicon surface, they dissociate and sulfur enters silicon. So they have demonstrated that in strong increase these spectra, so they have demonstrated, sorry for not very good quality, they have demonstrated the increase of absorption in near infrared range up to 2 and 2.5 microns. Actually, the produced structures looks very defective. Like here, this is a cross-sectional analysis by electron microscopy, and there is a necessity to make thermal annealing, so make thermal management of donor sulfur centers. Because after laser irradiation, the crystalline lattice is somewhat distorted, and electrical conductivity is very poor. So through thermal annealing, we can anneal the lattice to restore the lattice, but simultaneously people observe that annealing makes the donor effect in infrared absorption much lower. And so this story continued with optimization of, so people looked how the absorbance in infrared range around between 1 and 3 microns, how it changes versus temperature, and found that there is a strong minimum at high temperatures, which are typically used for annealing. So thermal annealing looks very bad for this kind of infrared absorption. So it's just cancels effect of doping. And to understand why this happens and how people can use this stuff, later people studied chemistry of sulfur, because sulfur, the absorption which was considered here and here in these experiments, this is absorption of single sulfur atoms. But sulfur can make clusters, and clusters are absorbing in further in infrared region, and this could be even more important. So if you look at chemistry of sulfur atoms inside silicon, we can use XPS X-ray photoelectron spectroscopy to consider chemical states of sulfur in sulfur in silicon. And people have found that at very high temperatures, like 1340 degrees, the total amount of sulfur centers decreases because of dissolution and evaporation of sulfur. And small centers like atomic center or diatomic, they also decrease in time, but simultaneously clusters, this is the same time scale, clusters are increasing in the dot layer. And this was later, this is year 2013, and later this was supported by XPS or even synchrotron studies in China. Yes. They have found in XPS spectra a number of components corresponding to atomic sulfur, charged sulfur, diatomics and aggregates, sulfur aggregates, which are called SN, where the numbers of atoms more than 2 atoms. So these are diatomics, these are charged atom, and this is neutral atoms. So these components can be considered as a function of pressure and temperature, and so there is minima and maxima, and so there are optimal conditions for each center. So it looks like increasing temperature makes the aggregation of sulfur atoms in silicon more advantageous, and this can be used for other purposes. And in our work, we have used lasers to scan silicon surface in liquid carbon dioxide. Carbon dioxide, this is the composition of carbon and sulfur, CS2, and it can be easily dissociated in carbon and sulfur. And when we scan silicon surface, we have 2 effects. We are producing surface nanostructures, dielectric nanostructures, and we introduce sulfur inside. So chemical analysis by energy dispersion spectroscopy indicates we have sulfur about 4% atomic percent in the surface layer. This is almost 10 times more than technology which was developed by Harvard University, because they have used gases. Gases are less dense comparing to liquid, almost 1,000 times less dense. So collisions of doping molecules with hot surface occurring almost 1,000 times rare. And so this technology is more intense in the sense of sulfur doping inside silicon. And as a result, we can introduce much more sulfur inside, almost 10 times more. As I told, 4 atomic percent in this case, but in some cases up to 8%. So the technology looks like when we are scanning surface, we are producing these periodic structures, and in these periodic structures, carbon occurs on the top of this, on the top as a carbon layer. Oxygen also oxidizes these silicon ripples, silicon spikes, but sulfur enters inside these spikes. If we again, if you look at TM pictures of these spikes, they are significantly amorphous because the technology assumes this kind of laser technology assumes redeposition of silicon ablated from valleys to these spikes. So we need annealing again, and we choose the right choose the right temperature for annealing to convert amorphous silicon to crystalline silicon, but simultaneously produce the right state of sulfur centers. And occasionally in our work, we have actually by the limit of our oven which we use for annealing, we have chosen this minimum of sulfur concentration and minimum of near-infrared absorbance. But we have got very just opposite and very extraordinary results in our case. So annealing, thermal annealing was done at 1200 degrees, and as a result of annealing we produced the almost flat silicon surface. So these kind of spikes were oxidized and just delaminated from the surface. So the sulfur was in the top layer of silicon. This is cross-sectional analysis. So the cut of silicon wafer. Silicon is here. This is oxide layer. Sulfur is in the top layer of silicon. Oxygen is on the top, and carbon is in oxide layer and above. So annealing, if you do XPS analysis of X-ray photoelectron spectroscopy analysis of annealed structures, we can see that sulfur is present in different compositions. It's on surface, the donor sulfur, which we need for infrared absorption, it is oxidized as sulfate ion or sulfite ion. But and this is very significant fraction here and here. But some sulfur is still present as atomic or in cluster forms, which is the fraction we can use for infrared absorption. So we have constructed photodiode using NP junction in very simple form. So we have used p-doped silicon substrate, and we scanned laser on its top to introduce sulfur. And sulfur is as a donor impurity and type impurity. So we have got NP junction in this case. This is some kind of primitive device made of just for scientific measurements. And we put this is the top view of this system. So we have p-type silicon wafer. We have square region of n silicon and n-type silicon, and we have electrodes to make these measurements. And in our case, we can see that photoconductivity appears in the range up to 400 reciprocal centimeters. So almost to 25 microns. So in far infrared range, and different types of sulfur complexes, which are S2, S1, charged or uncharged, they make their own absorption bands. So if we could ideally make just one type of sulfur centers, we would get just one band for specific absorption in specific region. I think this is potentially possible, but this is already issue of technology, not science. But we have demonstrated that it's possible to produce infrared absorption in very broad region, and we have studied current voltage characteristics of these diodes, and we show that with light in dark mode or light mode, there is a significant effect here. Okay, and what is interesting, I will just explain you a little bit the principle of this system. We have produced in the hyperdoped layer on the surface of silicon, we have produced different centers, which could be neutral or charged ones. Sulfur has 6 electrons, so it can be ionized twice. So the neutral center can give 1 electron to conduction band and change to charge center. Charge center could give another electron. Then it has just 4 electrons as silicon, no more electrons, no electrons more. So totally the sulfur can give 2 electrons. As one is neutral center and the second electron is a charge center. And near conduction band, see these centers depending on their size, atomic size S1 or diatomic size S2 or clusters. They occupy different positions, and infrared photons can be absorbed from these states to conduction band, and this gives the photoconductivity. This is experimental studies showing how photoconductivity can be it shows photoconductivity spectra at different temperatures, varying from 10 Kelvin to normal temperature, room temperature, or almost room temperature. And here we can see that versus increasing temperature, we have transformations of spectra. Photoconductivity maximum goes from infrared region to visible region. So temperature increases this way, and maximum are moving this way. And this happens because at low temperatures, these states, they contribute to photoconductivity. So by infrared photons, electrons are going to conduction band. But simultaneously, temperature promotes the same transitions. So the silicon temperature makes thermal transitions of electron to conduction band. And when temperature increases more and more states becoming ionized, here, and as a result, we have no transitions more, but transitions are possible for deeper states. And this can be illustrated here. So we have, as a function of temperature, we can see how spectra are changing. But what is interesting here, if we have ionization, for example, of this center, thermal ionization, it becomes state of like this. So number of states of this kind increases, and we see here as a function of temperature, the photoconductivity increases in some range until these states become thermally depleted again. Okay. And finally, we have done terahertz and far infrared spectroscopy on these materials on annealed, hyperdoped silicon, and annealed one. And we see that since the wafer, silicon wafer has polished faces, 2 polished faces, some wavelengths can resonate inside this wafer if the wavelength is comparable to the wafer thickness. And as a result, you can see these kind of oscillations. Oscillations which are not usually typical for infrared spectroscopy, but in terahertz range, terahertz photons are making interference inside wafer. typical wafer thickness is 500 microns, so wavelengths of tens or hundreds of microns, they can produce interference patterns inside. And what is interesting for annealed silicon, we have stronger modulation of transmission, and for annealed one, because of stronger absorption of sulfur impurities, we have less transmission, much less. And this is illustrated here, for example, in terahertz range. This is annealed silicon and transmission of annealed silicon, and this is transmission of an annealed one. And we can extract from this spectrum, we can extract characteristics like DC conductivity, scattering rate, plasma frequency of annealed silicon, unannealed silicon, and even bare silicon. So we can see that plasma frequency is significantly higher for annealed silicon, but scattering is comparable. Scattering actually even less gamma factor because of its annealed one. Annealed material is more regular crystalline lattice. Okay, so let's make a 2-minute stop at this point. If you have some questions, now we are going to laser effects inside materials. Previously, we have discussed how laser can dope sulfur to silicon on its surface, but now we'll go to bulk materials. We'll enter new defects in bulk materials. So this is the second part of my talk, and we have time for a few questions at this point. So if you have some questions for first part, you're welcome. Like in any seminar, I can ask questions for you, okay? Okay, let's continue. No questions. Light can produce, temperature or pressure, light can also produce point defects inside materials. Typically, this is associated with excitons. There are, again, two types of excitons. Frenkel exciton, which was invented by Jakob Frenkel in 1931. It's typical for molecular crystals because the exciton is actually the couple of electron and hole, negative electron and positive hole. And for Frenkel excitons, the size of the different distance between electron and hole is comparable to atomic to lattice crystallographic unit. So it's very small particle which occupies some crystalline site. And there are much bigger excitons which have size over many nanometers. So distance between electron and hole is very big, and it's called the near-mode exciton. This is typical for semiconductors, and we'll consider this kind of. You usually consider this kind of stuff, but to produce point defects, we are much more interested in the first one, which is untypical. To change the lattice crystalline lattice by electrons, we should consider electron phonon interaction or exciton phonon interaction. Phonon is the lattice vibration, and if we make this lattice very strong, in specific point, we can change structure. So these kind of interactions are called polaroids. And interactions which can occur between electrons or excitons and lattice are divided in a few cases. Product interaction, which is interaction with infrared active optical photons. Piezoelectric interaction with acoustic photons. And deformation potential interaction, which involves Raman active optical and acoustic photons. Polarons can be large ones, which are typically considered in terms of electrical conductivity in semiconductors, and small polarons, which are much closer to generation of point defects. So if an electron in the lattice can decrease its energy by moving atoms in some side away, so it decreases its electronic energy but increases elastic energy of lattice. And this happens through this electron-photon interaction. So initially parabolic potential changes to displaced one, so the lattice increases its energy because of this displacement, but electron decreases its energy just in this potential well. And this is described by these Hamiltonians through simple equations. There is a very simple Pyros model describing such transitions. If we have one-dimensional, one-electron metal, so this could be hydrogen or sodium atoms in regular lattice. One electron on each side occupies conduction band, so conduction band is semi-occupied, but this structure appears to be unstable to pairing, to coupling of atoms. So if each two atoms are displacing to make these kind of pairs, so the period increases twice, and in conduction band this results in band spectrum. This results in formation of field valence band and empty conduction band. So initial metal converts to semiconductor or dielectric in this case. And this could happen not only in regular way, but by any electron in semiconductor in each position. So this makes then not structural transformation, but makes the point defect. And this is typical self-driving mechanism. If we talk about now laser modification of impurity defects, we can consider two basic processes, like aggregation and dissociation. So impurity defects can aggregate just if we have laser heating of material, it increases, activates mobility of defects, and defects can come together and aggregate because typically they are stuck and it's difficult then to move in crystalline lattice because of lattice rigidity. Laser can produce pressure, local pressure, which induces reactions and transport of defects. Because if we have vacancy some kind of stick atoms making the rarefaction, and if we increase pressure, pressure induces more vacancies to come to this region to decrease pressure, local pressure. And on opposite, if we have interstitial, which is some kind of pushes the atoms in lattice away, high pressure is not favorable for interstitials, and external pressure makes interstitial to leave this region. So the pressure does not give not only reaction but also transport of defects. And finally, if we produce vacancies and interstitials by photolysis. These species can attach to impurity defects like in the case of nitrogen above. On opposite, laser can induce dissociation through activation of decay of centers and their mobility. Also, dissociation can occur through photochemical decay and vacancy-driven decay. And now, why we should use femtosecond lasers for this technology? Femto means 10 to the minus 15 part of a second, and picosecond 10 to the minus 12 part of a second. These lasers are very short, and only electrons can move during this, can be promoted during these pulses. So ions are remaining in the same positions. So this is purely electronic process. Later, of course, after pulse, ion can start to move, but just we address only electrons initially by these lasers. So because of these very short pulse widths, we have high peak intensity even at low pulse energies. Again, because of high intensity, we have strong linear or non-linear optical absorption by any materials. So even transport media, which are some kind of not absorbing at all, generally like a glass, window glass. If the femtosecond laser enters, focus femtosecond laser enters the window glass, it makes plasma so absorbing, so almost total energy can be absorbed and not go through. And this is because of very high non-linear absorption. Also, such pulses propagate not only in linear mode, like normal light, but also non-linear mode. So they can be self-focused or defocused in transparent materials. Furthermore, there are strong plasmonic effects. If we produce plasma inside glass, we can excite also plasmons on such plasma, and plasmons can interact with light or interact with each other to make interference patterns on very atomic scale. And finally, such lasers are producing non-thermal electron phonome interactions, displacement and deformation of crystalline lattice, source shock waves, and so on. So, in our case, initially we have applied these to diamonds, because diamonds, diamonds were called in some American movie girls' best friends, and we want to protect this right, because there is a lot of falsification of brilliance through producing synthetic diamonds. For example, CVD, chemical vapor deposition, can produce this kind of diamonds, red ones. And high pressure, high temperature technology, these big aggregates can produce very nice diamonds. But only cut natural diamonds are called brilliants. And so our goal was to make technology for tracing of natural synthetic diamonds through their bulk encoding. This helps to trademark protection and helps to work against illegal mining. Historically, we have used femtosecond lasers to produce graphitic encoding in diamonds, natural diamonds. So you can see this is graphite structures, microstructures produced inside diamonds, and they can be visible visible by just normal lens of jewelry laboratories. And here you can see the Raman spectrum showing the appearance of graphite band inside these diamonds. But this technology was also patented by Harvard University, so we have developed another technology which works with color centers or detects nitrogen aggregates in nitrogen. So such aggregates can produce luminescence in UV to near-infrared range. Here you can see the spectrum going from 300 nanometers to almost 900 nanometers with luminescence inside. And this technology was patented, and I can show you the short movie how it is employed by Russian company Alrosa for identification of diamonds. Oops. No sound. Sorry, unfortunately, you can just picture, no sound. But this is technology made in producing, changing nitrogen centers in diamond lattice, and this makes the new luminescent centers only where laser was going through. So the Gemological Institute of America was unable to find these centers. So they cannot, so this innovation goes beyond the standard gemologist technologies. So gemologists cannot observe this marking, micro marking. But this technology, which was made by our engineering center, it helps to use just QR coding. So diamond with QR code, micro QR code inscribed inside diamond. It's placed in this scanner, and scanner can show you the QR code, and you can read it with cell phone, and you can in the database of Alrosa, which is you can see the information about the diamond. Okay, but let's switch to the further. Diamonds, as I told, there are many different color centers, and so optical properties of diamonds are very different. So here you can see photoluminescence. There are four types of diamonds, and luminescence spectra are very different. They are low. This is logarithmic scale, so you can see some centers are low luminous and some high luminous. In UV, near-infrared spectroscopy, you can see that some centers are strongly present in transmission, and some are not. In infrared spectroscopy, it shows the abundance of different centers, and this is table showing that their content abundance can be very, very strong. But so if you want to focus femtosecond laser inside diamonds to produce this modification, to produce this atomistic transformation of color centers, we are going through the whole set of different physical effects like photoexcitation by laser, then we produce plasma. These electrons carriers can be recombined, can be fused away, can be self-trapped by lattice producing defects. Also there is a thermal step, diffusion or percolation, and this happens on this time scale from femtosecond to multiple picoseconds. For example, if we are focusing laser inside diamond, so laser focusing is shown here. The focus depends on the laser parameters, so the peak power of laser pulse. It goes from linear focusing, so this is focal position. So it
can be extended this way toward the laser because of nonlinear process like self-focusing. Probably this happens both for natural and synthetic diamonds. So nonlinear interactions related to nonlinear susceptibility like chemistry are very favored by color centers inside diamonds, but because of I should go to there, we'll skip this point. If the band structure, the gap between valence band where we have electrons and empty conduction band is very high in diamonds, up to minimum 6-7 electron volts, but could be bigger in some other positions. So if you use infrared photons with wavelengths 1 micron, we need 5, 6, or even 10 photons to promote electron from valence to conduction band to produce plasma. And this happens here. You can see the photoluminescence versus laser intensity, and the slope is very high here at the low intensities. Here we can see this kind of slope. It could be 20 or 10. So we need simultaneously to absorb 10 or 20 photons to promote electron from here to here. And because of symmetry of diamond, this process also anisotropic. So if we put laser polarization to promote electron here, we need less photons. If we put laser polarization in diamond cell in another direction, we may need more photons for this process. Okay. This is a simple kinetic rate model which explains the solid state dynamics, but I will skip it because of what we can do also to understand this process. We can do in situ. We can do in situ Raman scattering. So the same laser pulse which promotes electrons, it can produce Raman signal, and we can detect this Raman intensity and see how it changes for different pulse widths. Initially, it's strongly broadened to the red width, and this shows the photon softening because of plasma. And so we can evaluate concentration of plasma from these measurements. At later times, we can see the line splits into two components, and this component shows the local pressure, anisotropic pressure in the focal region. And we can evaluate this electronic stress considering the acoustic deformation potential and plasma density, and it goes to tens of gigapascals. Huge pressure, but very locally, only focal points, which has micron dimensions. At later times, we have phonons generated in the focal volume and anisotropic stresses and splitting of Raman line into three components. And at later times, we can see homogeneous broadening. Homogeneous broadening shows the stress is homogeneous, so there is just thermal stress around, and that's it. Now we can come to the atomistic transformation. The technology looks very simple. We just focus on laser inside the diamond slab, and we're producing the not quark, but separate dots inside the diamonds at different pulse energies and different exposures. So these are using different pulse widths. We can see that what's going on in this case is just changing spectra from dark green to light green. So this luminescence, this kind of luminescence is increasing corresponding to these centers, to the increase in the in the marked region. And similarly, we can see that these centers, their luminescence is decreasing. So there is conversion of one centers to other centers here. And recently in our carbon paper, we have shown that red diamonds can be converted, can be bleached by femtosecond laser. So it's initially a red one, but it can be bleached. And in infrared spectrum, we can see that C and A centers, which makes this red color, they decreased a little bit. There is the same changes in optical transmission, which occur as these marks. Diamond is not damaged because we can see the Raman in diamonds, reference spectra, and the modified regions show the same Raman densities, but the change of color, the bleaching results with decrease of NV centers, which are absorbing in the red region, and increase of blue emitting centers. You can see here the unmodified materials change to modified, so there is increase of blue emitting centers and decrease of red-green emitting centers. Okay. And the last part of my talk, I have maybe 5 more minutes. We will talk about nanostructure in bulk dielectrics, which is again related to defects, but now with some functional structures. Initially, the low energy inscription in bulk dielectrics by femtosecond lasers correspond to local densification in silica glasses. And this enables to write bulk waveguides, so people can scan the silica glass and write waveguide. Cross-sectionally, this is a more dense region. This is the refractive index profile, and it is related to modification of oxygen matrix in silica glass, the changing of oxygen centers. And using this technology, people can densify glass, and for example, in the piece of glass, make local densification in the form of hand. So this is a piece of glass with densified material in the form of hand, and other glass was removed by etching. So there is a millimeter scale glass hand. And later I will show you something more interesting. Another type of modification is local nanoablation. So people can, with femtosecond lasers, can produce submicron voids, empty spaces inside dielectrics. They are typically used for optical memory or just as separate bits. This is 2 micron scale, and this is submicron empty white inside. Or if we scan this in space, we can produce hollow channels. Hollow channels enabled to make blood vessels in these glass cans. So people first initially produce densified glass in the form of cans, and later made hollow channels inside and put a red dye as a blood inside that. So this is microscale technology. Okay. And finally, people can produce through non-destructive plasmonic pattern, you can produce birefringent gratings inside dielectrics, and this is typically used to produce polarization elements or other micro-optics. So if laser comes from this side, people can produce such whites or periodic sequence of whites
or even some more complicated structures depending on energy. And because of periodic structure in this direction, this bit of material becomes birefringent, so refractive index is changing in different directions, and people can see, for light coming through these regions, people can see phase shift. And we have studied this close. Oh, I probably can skip. This technology can be used also for electrical domain engineering in ferroelectrics, for example, to increase second harmonic transformation generation. In our work, we studied the same structure, so laser has really microbits of birefringent gratings in calcium fluoride. Calcium fluoride is a material making friendly pairs of fluorine vacancies and interstitials. So we use this to produce nanostructures. We use the different pulse widths and different energies to produce these kind of tracks. And these tracks are showing birefringence in polarizing microscope. So there is a change there is a difference in refractive index between ordinary and extraordinary wave. Okay, and we can see that this, as a function of energy, we can see this phase shift, and we can see the thickness of modified region by laser, and dividing phase shift by length, we can calculate the change of refractive index, and it is about 10 to the minus 3, and it's good to produce different optics. Probably I skipped the physical. Yeah, let me spend 2 more minutes. We have explained the mechanism of how these structures can be produced through producing plasma in focus, and the laser pulse can reflect from this plasma and interfere with incident pulse to produce interference structures like here. So you can see the laser pulse is coming from the top through photoresist, reflected by silver film, reflects back and interferes with incident pulse to produce this periodical modification, like here. And this, if we simulate plasma as a reflecting ball, we can see that these periodic structures appear just in front of this plasma ball. And as a result, we can see this kind of modification in this region. And this modification gives us birefringency. We can do modeling in terms of interfacial plasmons. And we can predict actually the properties. So I will go probably different applications of this kind of gratings. For example, using this technology, nanopatterning, birefringent nanopatterning, we can write Fresnel lens. You probably can see some rings here, which are not very clear just in white light transmittance. But if we use cross polarizers, you can see the embedded Fresnel lens. And also we can put polarizing, using this birefringency, we can make polarizing spectral microfilters. So using two types, two polarizers in transparent material like glass, we can produce color filters. So see here we have just glass, a piece of glass, and if you use polarizer to see, to watch inside, we can see inscribed figures in color. And this technology can be used for microspectroscopy. If we
put a microfluidic channel here and some birefringent structures in front of it, we can separate colors in the bulb. Using white light, we can separate colors and use it for microspectroscopy. This is our collaborators in this work, company Alrosa, and different Moscow State University and Bonn State Technical University. And sorry, thank you for some extra time. I will be happy to have your questions. Thank you.
Các bạn thấy có hay không? Hay đúng không? Thực sự là hay, thực sự là hay. Yeah, thank you, Professor Ultrashort. So actually, I know you. I think almost around 5 years ago. I know you. Yeah, and we have. I think we have two projects. One project together. Is correct? Yeah. Tức là tôi thì cũng hợp tác với giáo sư này được khoảng 5 năm và đã có hai đề tài thành công. Okay. Sorry, I have to introduce you Professor Phan Hồi from the Institute of Material Vietnam Academy. Các bạn, đấy cũng là một trong những ứng dụng của laser. Laser thì có quá nhiều ứng dụng đúng không? Và chiều nay các bạn sẽ nghe một bài giảng về laser và cái nhóm của giáo sư Ultrashort để sử dụng các bạn laser với các công suất, với các thông số ví dụ như là femto, nano, pico khác nhau để chế tạo các vật liệu nano hoặc là chế tạo một số cái vật liệu tức là cái vật liệu khác nhau. Tôi nghĩ rất là hay. Đây là một cái hướng mà ở Việt Nam mình bây giờ cũng có một số nhóm mới bắt đầu làm, nhưng mà để mà làm chuyên sâu thì còn cần có thời gian. Các bạn có câu hỏi nào không? Any question, please?
Actually, some time ago in my lab, two Vietnamese students have got PhD degrees.
Yeah.
This students now in Vietnam, but
Yeah.
Yeah.
Tức là nhóm giáo sư cũng đã đào tạo cho hai tiến sĩ ở Việt Nam, một tiến sĩ Lượng, Lượng thì làm ở Viện Pháp ở Hà Nội, và thứ hai là tiến sĩ Trang thì đang là giảng viên của Đại học Hà Tĩnh. Các bạn nhé, các bạn có câu hỏi mạnh sẵn đấy. Cả ai có tiếng Việt cũng được, chúng tôi translate cho các anh không? Nhưng mà
So you are welcome for PhD positions and training in our lab.
Yeah. Thực chất là một nhóm mà đã làm việc với người Việt Nam thì người ta rất quý người Việt Nam, và ông cũng nói là các bạn hoàn toàn welcome các bạn mà sang làm PhD ở bên Nga. Thì okay. So, em không hỏi gì không? Okay, so it's okay, if no questions, so maybe we thank Professor Sergei Kufro. Again. Yeah, Professor. Okay, so các bạn bây giờ lại có cơm trưa của ban tổ chức khoa học ở bên phía ngoài, và các bạn nhớ là chiều nay là chúng ta quay lại lớp học 1:30 về cái bài giảng của tiến sĩ Đỗ Hoàng Tùng về công nghệ plasma ứng dụng, và sau đó thì đến 3 giờ chiều 3 giờ Việt Nam thì đó thì chúng ta sẽ quay lại thứ hai.